This is an example here of sort of the complication level that circuits can typically become as you take sort of an introductory electricity and magnetism course, perhaps in college or high school physics. You look at the circuit here, it has 2 batteries and 3 resistors, and there is no way of quickly simplifying this to make finding any one of the currents easy here. Like, for instance, these 2 resistors here might look like they're in series because they sort of go across like that, but in fact they're not, because at this junction point between the resistors here, there's another resistor. In other words, there's another path that the charge can take as it goes through the resistors like that, so they're not in series. You might think that maybe this one and this one are in series because it goes around like this, but if it's not, because there's a resistor going off this way. You might think these batteries are in parallel, or might think many things, but all of them are false for a circuit like this. There's actually nothing you can do other than a full analysis over this using the junction and the loop rule to get this circuit to work. But what you do, though, is just fall back on some things you know. So here's what we know. I know that this is a battery here, and I'm going to keep it all symbolic here. You could easily put a 9 volt and a 6 volt in here and put some actual numbers in for the R's, but we'll just do it sort of generally here to get the lessons across and do it in terms of symbols. So what I know is going to happen as soon as this circuit is turned on is that current is going to begin to flow out of this battery here. And since it doesn't have a choice of where to flow around this loop here, just start flowing here. And this is sort of going to stop right there. And I'm going to label this I1, as in current 1. Now the reason why it's going to stop right here is because there's a junction here. Okay? So when current comes to a junction, what we know is the amount of current that flows in must flow out. But it can't be I1 flowing out because it has to split. Some of it will go this way and some of it will go down. It remains to be seen exactly what those ratios will be. But in either case, current I1 will cease to exist at this junction. Instead, it's going to split into I2, which is going to go down this way, and I'll call it I3, which is going to go down this way. So I3 is going to be the one that goes right down through this central leg here, and I2 is the one that's going to cover this loop over here. The reason why I2 can cover this whole loop over here is because it doesn't have any choice. It has to go through the resistor, through the battery, back around, and back to this other junction right here. So I2 is actually the same current that's going to travel all through this loop here and go around like that because it doesn't have a choice. It has to follow those wires. I3 here will start at this junction and travel just through this resistor here, but it'll stop when it gets to this junction right here because it splits again. And you might be thinking, well, I need to label more currents and stuff, but you don't, because remember that it's I1, which is sort of flowing through this section of the circuit over here. Initially, I just drew it going through this resistor, that because there's no choices about which direction to flow here, it must be I1 that came out of the battery, went into the battery, and even came from this section of the circuit here. So I3 is going to split at this junction into I1 this way, which we've already discussed. It can also split and go this way, but I2's got that section covered there. So it's really just 3 currents. And here's how the junction rule works, which we discussed in a previous video, but we have not used until this point right here. There's a big junction right here. And just to remind yourself that it's a junction, it's a good idea to draw a big dot there because it's exactly where current goes in and it comes out, but that's where that junction rule, that what goes in must come out, definitely holds. So at that junction right there, I see I1 flowing in, and I see I2 and I3 flowing out. So this is actually an application of that junction rule, that what flows in must be what flows out. So I1 is I2 plus I3. There you go. Okay? So now you still don't really have enough to make any calculations with. I certainly can't determine I1, 2, and 3. It is an equation, but it involves 3 unknowns, and it's only 1 equation, so algebra tells you need to generate at least 2 more equations in order to solve this thing. But we can do that using the Kirchhoff's loop rule here. In particular, that the sum of the voltages on a loop are equal to 0. So I have all my currents going in there, but current loops and these traversal loops aren't necessarily the same thing. They can be, but not in all cases here. So what we'll do, let's just set a loop that goes around this circuit like this. I'm going to start at this battery, and I'm going to go all the way around the loop like this, and end up at the battery. Remember, the only definition of a loop is that you start and end in the same spot. You can traverse the circuit any way you want. So what I'm going to do now is I'm actually going to pretend that my little person out here walking my dog, and I always walk along my traversal loops here. I'm not a current loop. I'm not like one of those red lines in there. I'm actually just going to walk along now and sort of see what voltages and things I encounter. And in order to get around to where I started, I'll make sure that all those encounters or voltages add up to 0. So first thing, it's like walking the dog here. I go across the battery. It's like I leave my front door and I immediately have to walk up a hill. I have a plus V1. Rise in voltage as I go up like that. As I head across this resistor here, as we discussed in a previous video here, it looks like I'm sort of walking in this direction. I'm encountering a current that's in the same direction that I'm walking here. So there I am walking to the right, and the current's to the right. that means I'm going to witness a drop in voltage across this resistor right here because of all the banging around that goes on in there. So my next voltage will be I1 times R1. Remember, that's an application of Ohm's law. Remember that V equals IR, not the most intuitive form of Ohm's law, but it's what we're going to use here. So there's my I1 R1 drop across the top resistor. I continue now along my orange path. Remember, I'm ignoring the junction because I'm not saying that this path is where current flows. I'm just saying this is how I'm choosing to walk around the circuit to inspect it. So I just keep on going, even though there's a junction. I keep going, and I encounter this resistor here. And again, I'm still walking towards the right, and I encounter I2 going through R2 to the right also. So that's another voltage drop. I'll see a minus I2 times R2 in there. There's another voltage drop right there. So see, I'm forming my Kirchhoff's law equation. And here I go across this battery here, and I'm going from the positive to the negative. It's like walking downhill, so I'll see a drop in voltage right there. I'll see a minus V2 as I go down like that. And as I continue my loop, I don't see any other components here, just straight pieces of wire which have no voltage drop, and I go right back to the battery, so I'm done. I have another equation equals 0. There's an application of Kirchhoff's loop rule for that outer loop there. I need another equation, though, because remember my original junction rule generated 3 unknowns in one equation. Here's another equation that involves I1 and R1, so it's almost enough to solve, but not quite. So I need one more equation. So I need to find one more Kirchhoff's law loop that I can sort of traverse through, and I'll just choose this one right here. I'll choose to go around this one right here. Again, not current necessarily. I'm just taking a walk with my dog. I'm going to walk around that purple loop now. Let's see what we get when we do that. Okay, so here we go. Again, I come out the door, I go uphill, I see a plus V1. Keep walking around the loop here. I'm going to cross another I1 times R1. I'm walking in the same direction as the current flowing through I1, so I'll have the sign there. I1 times R1. You're probably dying to know what would happen if I went across a resistor in a direction opposite to its current flow. Well, I wouldn't see a minus I1 R1. I see a positive. So I see a positive IR1, and we'll try to do that in that last loop there. But for now, when I'm in the same direction as current flow, I get these minus signs. Continue along here. I'm following my purple loop. I hit this resistor, now I hit this one. I have an I3 and an R3 going through it, and it looks like I'm walking in the same direction as I3, so minus I3 times R3. There's my next term. Keep walking around the purple loop. Nothing, just a bunch of wire and a junction, and I'm back to the battery, which I've already analyzed, so I get 0 for that. There's another application of Kirchhoff's loop rule, and these three here are giving me sufficient equations to solve for the entire system. So as an example here, suppose we just put in some values here. Suppose that V1 in this circuit here was 10 volts, and suppose V2 was 6 volts, and say R1 was 2 ohms, and R2 was 10 ohms, and R3 was 5 ohms. Suppose you had those numbers now. These three equations here would allow you to solve for exactly what the current flow here, I1 is, I3, and I2. But we're trying to keep it general and just get some ideas about this loop rule out, so even though we don't need it, we can stop there. The problem's solved. Suppose I also just want to choose to go through this loop, and for the sake of just highlighting this sign issue that comes up here, let's just traverse the loop in the counterclockwise sense. Let's go around this way. Again, I'm going to start here, like I'm walking my dog, and I'm going to walk counterclockwise this way around that loop there. So what am I going to get? As I start here, I just sort of keep walking here, and I hit this battery here. It's a rise in voltage, plus V2. So I'll see a plus V2 as I hit that battery right there. Now as I keep going around this loop here, I have a current I2, which I've drawn flowing to the right, but I'm traversing to the left as I go around my green loop. So I'm going opposite the current. And what that means is, unlike these two examples here, instead of generating a minus sign, this can generate a plus sign. It's going to be plus I2 times R2. I'll actually be going sort of against the current, like salmon swimming up the stream. In norm spawning surface here, I'm actually going to have a rise in potential. I go across this resistor here, so I get a plus I2 R2, not a negative. Now, don't get distracted though. Continue on with your loop. You're going around down this resistor here. Looks like the current is down and I'm going down just like before. So I will get a minus, it's I3 flowing through the resistor R3, and then I'll go back around. And then of course I back around the end of my loop, so I get a big equals to 0 in there. So I'm done with this loop here. So I like this last loop here because it gave us a bit of contrast in the way those signs work in Kirchhoff's junction, in Kirchhoff's loop rule here. This is the positive sign here because I was walking opposite to the flow, and this is the negative sign I got here because I'm going with the flow of the current there. So you have to be very careful about that, because obviously when you're forming these equations, any little sign mistake will make the whole thing wrong. So in either case, I really overanalyze the problem, but you can choose any three of these equations here if you know the voltage and the resistance the way I've discussed here, because ultimately your goal here is to find I1, I2, and I3. You'd like numerical values for those currents, and these equations will deliver them to you. So hopefully you got that then with Kirchhoff's rule. The junction, what flows in must flow out. That was a very easy one to form right at the beginning like that. And the other one is Kirchhoff's loop rule, which says isn't necessarily a current loop, it's any loop you want. So I just configure some arbitrary loops. I had an orange loop, a purple loop, and a green loop. I walked around them and just inspected what components do I encounter and what voltage change can I write about these encounters. Sometimes it was a rise, sometimes it was a fall. Batteries are particularly easy because you can go from the negative plate to the positive plate or positive to negative, depending. And you have to be careful about the current flow through the resistors. If you happen to be walking with the current flow, it generates a bunch of minus signs. If you're walking against the current flow, it generates a plus sign. But you get these nice equations which you now solve. You can plug in your calculator or Mathematica or whatnot and get currents to pop out, and those are usually the answers you want.